So Newton's first and second law go together pretty well. Where Newton's first law just tells us objects want to keep moving or want to stay still until a resultant force acts on them. What Newton's second law does is it tells us what the effect of that force actually is. So this goes back to the idea that forces cause things to accelerate. That's what we're really concentrating on, which means pretty much you can sum up Newton's second law as an equation. This is the F equals ma equation. So you'll be using this one quite a bit. Go back to the example we've already looked at, where an object is being pulled to the left and pulled to the right. The forces will partially cancel out, just leaving this 2 Newton force to the right. And it's that causes the acceleration. It's not the 4 Newton or the 2 Newton original force. So although this is a really big force to the right, it's not that causes the acceleration. In fact, we could change these forces for something much larger. The resultant force would be exactly the same. The two forces would all but cancel out. One of them is just 2 newtons bigger. And the acceleration of this would be the same as it was in the first example. It makes no difference how big the forces are. What matters is what's the overall effect after you've cancelled them out. So let's just have a look at how resultant force, because that's just a calculation, they're very easy to do, but what the effect of the resultant force is given directions. This can cause an awful lot of confusion. So the first example is nice and easy. You've got a resultant force, and the ball to start with is stationary. So this, hopefully, obviously, is going to cause an acceleration in that direction. The ball will get faster, and it'll get faster that way. In the second example, the ball's already moving. What happens if you apply a force to it in this direction? Again, it will accelerate this way, and it will get faster, but it was moving originally. Let's say it will get even faster. Okay, what if we apply a force against the direction of the ball? So this is what we would call deceleration. It's going to accelerate. Now, the direction we would say is this way. We might say deceleration, but this can get a bit confusing. You'll see why in a second. What it's possibly better to think of this as is negative acceleration. All right, really quickly, let's look at some numbers. 2 meters per second squared. What does that really mean? The speed is going up by 2 meters per second every second. That would be another way to write the same thing. 2 meters per second every second. The speed goes up by 2 every second. That's what that's saying. In this case, we might say it's minus 2 meters per second squared. That's saying the same thing, but in reverse. The speed is going down by 2 meters per second every second. It's a deceleration. The speed is getting less. It is slowing down. All right, let's just complicate things a little bit. Look at a situation where the ball is now moving the opposite way, but the force is applied to the right. So notice the directions of the arrows in this diagram. What would happen here? It's a really good idea to pause the video at this point and see if you can answer this question before I do. So this is the same situation as the one above if you think about it. The acceleration is always in the direction of the resultant force, so it is going to accelerate this way. But it's moving in the opposite direction. The acceleration is the opposite to the velocity. This is where it gets a little confusing. We might class this as positive acceleration just because it's to the right, and we'll take anything that's to the right as being positive. But this would mean that we are adding 2 meters per second to the speed every second. But remember that the velocity is to the left. So the velocity is negative. Let's say the velocity might be minus 10 meters per second at the start. We're going to add 2 to it. So what will it be a second later? It'd be minus 8, then minus 6, then minus 4. The negative just tells us what direction it's going in, but this is also causing it to slow down. So this is where we have to be really careful. The idea of positive and negative acceleration, you've got to consider, well, what was it doing to start with? Positive acceleration or negative acceleration doesn't necessarily mean it's going to speed up or slow down. Is the acceleration in the same way as the velocity, or is it working against it? That's what decides whether it speeds up or slows down. All right, so in this final example, we've got a negative velocity again. So let's imagine again, that this is minus 10 meters per second. We've got the force to the left, so in the same direction as the velocity. So this is exactly the same as the very first situation, or that situation, but just going the other way. Now, the acceleration is in that direction. It is a negative acceleration, which would mean we are taking 2 meters per second off it every second. But it's already on minus 10. If we take another 2, we get minus 12, minus 14, minus 15, so on. 16, whatever. In this case, what we're doing is we're accelerating to the left, but we are speeding up. This is a kind of strange situation, and it only really matters when you get into sort of numerical problems with it. But it is an important concept to understand what the effect of force is on acceleration and what the effect of acceleration is on velocity. Okay, here's a little mistake not to make. What people quite often assume is that if they are pushing an object and then they let it go, that object keeps moving, that they are somehow still applying a force to it. You are not a Jedi. This is not, unfortunately, true. In this instance, if this person pushed the box and then let it go, this force would not actually exist. The only force on the box that would happen as it's sliding across is a frictional force. This would cause the box to slow down and stop. The box will not keep moving because you're still pushing it. Once you stop touching it, you are not applying a force on it. And don't forget, the whole time, we've also got the weight and the normal reaction force from the floor.